we're going to pick up where we left off last time. Last time we talked about what it meant to be the component of a graph. And now we're going to pick up and talk about a special kind of family of graphs called the complete graph on n vertices. And the name for those are Kn, where n actually denotes how many vertices I have in my graph. So I have n vertices. What does it mean to be a complete graph on n vertices? The answer is it has to be a simple graph first. That means there are no loops or parallel edges. And then secondly, any two vertices have to be adjacent. Recall, two vertices are adjacent if there's an edge between them. All right, so Kn is a simple graph on n vertices such that any two vertices are adjacent. Now that turns out to be enough information to tell me exactly what the graph looks like. So here are a series of Kns. One I have not drawn is K0. It does exist. And what is K0? That's the graph with no vertices. And if it's got no vertices, then it also has no edges. And so it's a picture of nothing. That's why I didn't draw it. When n is 1, the complete graph on one vertex is denoted K1. And what does it look like? It just has one vertex. By the way, it's true that any two vertices are adjacent because I don't even have two vertices. So there's K1, just one vertex. What does K2 look like? Well, K2 has two vertices. And remember, any two vertices have to be adjacent. Also remember, it's got to be a simple graph, so I cannot have any loops or parallel edges. So that means K2 looks exactly like this. Two vertices and an edge between them. Okay, what about K3? Well, K3 is three vertices, and remember, any two vertices have to have an edge between them. So K3 looks like that. It turns out to have three vertices and three edges. K4, well, now I have four vertices. And remember, any two vertices have to be adjacent, so I have to draw an edge between any two vertices, and here's what a picture looks like. By the way, remember with respect to a graph, it doesn't matter where my vertices are, I can draw them anywhere in the plane, so the same graph might look very different. Notice right here in the middle, there is no dot. That means there is no vertex there. And what this structure here, where lines cross, edges cross, but there is no vertex, right, is special. And I'll talk about that next. All right, so there's K1, K2, K3, K4. You'll notice that K4 has how many edges? 1, 2, 3, 4, 5, 6. So K4 has 6 edges. All right, that's what it means to be a complete graph on n vertices, Kn. Now we're going to talk about what it means to be a planar graph. Well, a planar graph is one that can be drawn, and that's the key, without edges crossing. Up here in K4, you notice I have edges crossing. That does not mean it is not planar, because if I can draw it somehow without edges crossing, then it's a planar graph. All right, so what graphs are planar? Well, there's a planar graph. K1 is, K2 is, K3 is, there are no edges crossing. K4, it's not clear, but now let's go down here. Instead of drawing K4 like that, I can draw it like that. Do you see? Those are the same graphs. What do I mean by that? I mean the same vertices are connected by an edge, right? So even though these look different, they really are the same graph. And if you look over here, I have drawn it without edges crossing. So what does that mean? That means that K4, which is this right here, also this one, is planar. Why? Because I've drawn it without edges crossing. So there's the concept of planar graph. Now let's talk about what it means to be a bipartite graph. All right, so a graph is bipartite if the vertices can be divided up into two disjoint sets, right? So these two sets cannot have any overlap, such that what? Every edge is incident on vertices from both sets. What does that mean? It means that every edge has to have a vertex for both sets. By the way, one of these sets is allowed to be the null set if I want. And if that's the case, then you should see that K1 is in fact bipartite. I could, because I have one vertex, I could put it in one set. My other set of vertices is the null set. And it's true, every edge, of which I have none, is incident with vertices for both sets. What other graph is bipartite? Well, K2 is bipartite. How do I see that? Well, I put this vertex in one set, this vertex in another set, and it's true, every edge is incident with vertices for both sets. All right, now let's go down here to this graph right here. By the way, this is not K4 because I don't have these edges in here. I claim that's also bipartite. Now, how would I show it's bipartite? Well, I want to divide the vertices up into two sets, big V1 and big V2. And those two sets, what, are not allowed to overlap. And it must be true that every edge is incident with vertices from both sets. So here's the way I could do it. Let's put this vertex in the first set, big V1. So I put small v1 into big V1. I'm right there. Now this edge has to be incident with vertices for both sets. And so does this one. So if small v1 is in one set, small v2 has to be in the other set. So that makes small v2 in the other set. But since small v2 is in big V2, and there's an edge between that and V3, V3 has to be in the first set, because this edge has to be incident with vertices from both sets. Okay, so that puts V3 in the first set. But if V3 is in the first set, since it's connected or incident with V4, then V4 has to be in the set opposite V3. And now I've got V4 in the set opposite of V3. Notice there's an edge between V4 and V1. That means V1 cannot be in the same set as V4, so I put it up there. Or it's already there. So do you see? I've divided all the vertices up into two sets. They are disjoint. And every edge is incident with vertices from both sets. So what does that mean? That means this graph is bipartite. All right, now let's look at K3. That's that graph up there. I'm going to claim K3 is not bipartite. Okay, why? Well, here's my argument. If it is bipartite, then I have to put V1 in one of those sets. So let's put it in big V1. Now, V2 has to go in the other set. So V2 has to go in big V2, just like we had over there. V3 now has to go in the other set, but the other set is the one that has V1 in it. See it? But V3 cannot go in the same set as V1, because if it did, this edge would not be incident with vertices from both sets. So you see, this is not bipartite, while this one is. Now, later on, we're going to have a theorem that's going to tell us when a graph is bipartite and when it's not. For right now, I'm just doing those few examples. All right,